Hello, pre-calculus. So today we're going to be going, finishing off the handout here. We're going to have these identities. I want you to memorize these identities. We're going to go through the proof of these three right here. If you want to go through the proof of this last one, I'll let you do that for yourself as an exercise. But these three we're just going to run through. These are very important that you have, all of these memorized as they come up time and time again, not only in this class, but in Calculus 1, and also if you're in economics, biology, finance, they will come up again anytime where the exponential function is used. Also make sure you understand why these functions are inverses, and also make sure you understand how this definition works, right? We talked about that in the last video. If you're still not clear, go back and watch that video until it does make sense. So now let's go on to this one. First thing we're going to do is we're going to prove this guy right there. I'll kind of zoom out over here. Get out a separate sheet of paper if you don't have it already, and just kind of work through the proofs with me. Make sure you hit the pause button if you get if I start moving too fast for you, or if you need a second to ponder what I'm doing. Okay, so first off, we're going to start off by saying LHS. What is LHS? LHS is the left-hand side. So we're going to look at the left-hand side first. And so that is the log base b of mn. Okay, and so we're going to try and show that after all this long list of things that the left-hand side equals the right-hand side, right? Left-hand side equals the right-hand side, then that means the proof is true. So we're working towards that point. First thing we want to do is we want to make a clever substitution. We're going to look at this big M, and we're going to make a definition. We're going to say let big M equal b raised to the little m, right? That's how we're defining little m. And so if you take log base b of both sides, then you'll get little m on the right hand side of this definition here. If that doesn't make sense, press the pause button, work through it until it does. Alright, so next one. Alright, so the other definition we're going to do is to help us out with this in right there. We're going to say let big N equal b raised to the n. Take log base b of both sides, and you'll get little n like that. So it's just the same thing. So no, bn is this guy here, and then big M is this guy right here. So let's make that substitution. So this equals log base b of b raised to the little m multiplied by b raised to the little n. Okay. All we've done is we've just substitute in those two guys that we did. All right, next one. We're going to go ahead and combine these two. So this is going to be base b of the m plus n, right? That's how exponents work. If the bases are the same, you just add the exponents together. And so now, note right here, what are we asking? We're saying, what base do I have to put on this b right here to get b raised to the m plus n? Well, of course, the answer is little m plus little n. Now we've got expressions for this, right? Little m is this guy here. And then little n is this guy right here. So far, so good. So we just substitute those guys in. We got log base b of big M plus log base b of big N, right? That's all we're doing is just doing the necessary substitutions. And you might notice that this is the same thing as the right-hand side. So we say equals RHS. Left-hand side ultimately equals the right-hand side. We've made our proof. Very good. So now let's look at this proof right there. That's one we're going to prove, and we're going to reuse this definition that we've had right there. Okay, let's call this one 1. We'll call this next one 2. All right, so once again, we start off with a left-hand side. Left-hand side equals log base b of m with an n exponent on there. Okay? And so we're going to go ahead and make a similar substitution. I'm going to even use the same color highlight. All right, we're going to replace that with b raised to the m. Like so. And now we combine our exponents, so we get log base b of b raised to the m times n. And so now we go, okay, well, what exponent do I have to put on this b to get this guy here? Well, the answer should be obvious. It is m times n. Like that. And what is that little m? Well, we've already defined that in yellow up here. I'm going to go ahead and put this in front first. Just reverse the order, no big deal. So we have log base b to the big M. Okay. And note that is the same as the right-hand side. All right, so we've done the proof. All right, so go ahead and when you look at this, note that this takes multiplication and turns it into addition. And note this takes an exponent and turns it into multiplication, right? It's making whatever operation you're doing and making it a little bit easier. Now it can go both ways. I should probably do a double-sided arrow here because it does go in both ways. All right, so we're going to go to the third proof. The third proof is actually the easiest one because it uses the two proofs that we've already done, so we don't have to make any new definitions. And so let's come over here. We're going to do 3. And so once again, we start off with the left-hand side, which is log base b with a big M over big N. Okay. So now what we're going to do is we're going to break this up. We want to bring that N up into the top, and to bring it in the top, we just need to put a -1 exponent. No big deal. And now, we're going to go ahead and use 1, right? We're going to use this theorem right here. We're going to turn this multiplication into addition. So we got log base b of big M plus log base b of n raised to the -1. Now notice, we get a -1 exponent. We can bring that out into the front. So and that's going to be via 2. And so we have log base b of big M minus log base b of big N. And note that is the same as the right-hand side. So pretty nice. Okay, so hopefully in going through the proofs, you've also gotten a better idea of how the proofs work. I'm sorry, how these rules work by going through the proofs. You kind of understand how each of these theorems works a little bit better. This one, I'm just going to show you a little bit, this one right here, I'm just going to show you how it works rather than run through the whole proof of it. This is just if you have something that's of a base that you're not really used to. Say you got log of, let's just say 13 of 10. Well, how would you figure that one out? Well, you use this formula here, right? So we go, okay, 13. All right, that's our log. So it's going to end up coming down here. And then our 10, that's the same as this guy right here. So that's going to end up right here. Now, notice I haven't highlighted B. B is simply the base that you want. B is the base that your calculator does. And the one that your calculator does is either going to be 10 or E. It's either going to be a common log or it's going to be a natural log. So if we wanted to pump this into our calculator, we would do it like this. And since we got a 10, we're going to go and just use a common log. So it's going to be a log of 10 divided by log of 13. Okay, and so log of 10, that's just 1, so this ends up being 1 over log 13. If you want to get a decimal approximate, just plug that into your calculator, and that's how that one would work. This guy, if you just want to look at it in terms of the natural log or the common log, we can restate this. This is either going to be, they both start off the same log C of m, and then this would be common log of m divided by the common log of your whatever base you were working with before, or it could be the natural log of what you're trying to find divided by the natural log of whatever that previous base was. And that's, if it's easier to think of it in that way, just think of it in terms of that way. But this is how you would get a decimal approximate of a logarithm that's not easily calculated. All right, so let's get some practice with these guys. So first off, we're going to use one of the rules here. Note that this is the same thing as rule number 3. So we're going to use rule 3. And so we're going to turn the subtraction into division. So we'll take the natural log of 6x divided by x plus 1. And that equals the natural log of 4. Right? We got a logarithm on both sides, but they both have the exact same base. So we're going to raise everything by e. And so since the bases are the same, they go away. So we have 6x over x plus 1 equals 4. So this is a type of problem that we have a lot more experience with. So we're going to go ahead and work this one through. Multiply both sides by x plus 1. We get 6x equals 4 times x plus 1. Go ahead and make sure you can see what's going on here. We're multiplying both sides by x plus 1. All right, and now we just start solving for x. All right, now we subtract 4x from both sides, and we get 2x equals 4. Divide both sides by 2 to get x equals 2. All right, so go ahead and box that. That's our answer. Next one. Well, first off, we need to make sure we can see that the square root is really a 1/2 exponent. I want us to keep that in mind. But first things, let's go ahead and use that rule. So we've got log 16 of x plus 1 to the 1/2 power, and that equals 1/4. So that 1/2 comes to the front, so we have 1/2 times log 16 multiply by 2 like so. Now we want to get rid of the logarithm on the right hand side. How do we do that? We're going to apply the exponential function, and we're going to use a base of 16 on both sides. And so now we have x plus 1 equals the square root of 16. Square root of 16 is 4. Subtract 1 from both sides, and we get that x equals 3. Let's go ahead and just double check this one. That way you've got a little practice doing that. I'll do this in a different color. We'll use the blue pen. Plug that 3 into the left-hand side. Log 16 of 3 plus 1, that's log 16 of the square root of 4. Which is log 16 of 2. And so what exponent do I have to put on 16 in order to get 2? Well, it's going to be 1/4, right? A cubic root. I'm sorry, not a cubic root, a fourth root, which is the same as the right-hand side. Okay, and one of the ways you can figure that out, you take 16 and you start branching out like this, factor out a 2, and so then you have an 8, factor out another 2, you get a 4, factor out another 2, and you get a pair of 2s, right? So you've got this is 2 raised to the 4th. So if you were to take the 4th root of 16, you would get 2, which is exactly what we're showing over here. All right, so that's how you would double check your work. Okay, and again, that's just a check calculation, which verifies that we did in fact get 3. Problem number 3. So first thing we're going to do is we're going to use rule number 3, right? We're going to use rule number 3. So this 2 comes out into the front. And so we have 2 times log of x equals log of x, and this whole thing is squared. Okay? So now we're going to divide both sides by log x. All right. I want to do a quick aside for a second here. If you say you have log of 5, I have a concern that some of you might look at this and go, oh, logs cancel out. Answer is 5/2. That's wrong. That's not correct. Okay? You cannot cancel out logs in this fashion because log is a function. It's not a multiplication, right? So this does not work. Do not do this. All right, so I just wanted to make sure I cover that because I have seen that on exams that I've graded in the past, and I don't want any of you guys making that same mistake. All right, so here we can definitely cross out the entire thing, right? That's how that works. You can't just cancel out the log, but if the whole thing is the same, then you can cancel out on that basis. So it's log x gets rid of that 2 because that 2 means that we have 2 log x's up top. All right, so what do we have here? We've got 2 equals log base x. What is the base in that logarithm? It's 10. So we're going to raise both sides by 10. Or should I say, the base will be 10 when we apply the exponential function, would be the proper way to say that. So what is 10 squared? 10 squared is 100. And the right-hand side just becomes x. So the answer is 100. And that's it. That's your answer. All right, number 4. We're going to use rule number 3. I said rule 2 on this one. I'm sorry, that was rule number 2. We'll use rule 3 on that one. Rule 1. There we go. And that's, because we've got an addition going on here. So let's go ahead and take these two guys. And it's not very important that you remember what's rule 1, what's rule 2. What's important is that you understand how the rules operate and when to use them. So we're going to combine these two. This is addition, and it's going to become multiplication. So we get log base 9 of x plus 4 times x minus 4. Okay? And we got a monkey wrench over here. We got this crazy log 23. What exponent do I have to put on this 23 to get 23? 23 needs an exponent of 1, right? So that just equals 1. Good. Let's go ahead and get rid of that logarithm by applying the exponential function. And so we've got x plus 4 times x minus 4 equals 9. So far, so good. Let's go ahead and work this left-hand side. These are conjugates, so we get x squared minus 16 equals 9. Add 16 to both sides, we get x squared equals 25. Take the square root of both sides, x equals positive or negative 5, right? Because you want to do positive or negative when you take the square root. Now, question. We have two numbers, positive 5 and negative 5. Are both solutions valid? They could be, but maybe they're not. So if we plug in positive 5, then we're taking, this would be log 9 and log 1, right? Those are perfectly acceptable numbers to work with. I can take logs of positive numbers all day long. Now what about negative 5? You plug negative 5 into here, I'm taking the log of negative 1, and then I'm taking the log of negative 9. I cannot take the logarithm of negative numbers in this fashion, not unless there's an absolute value sign here, and there is not. So we would have to strike out the negative 1, and so the answer is simply positive 5. Okay, so that's that one. All right, so now we're going to go on to the word problems. Everyone asks for applications, but when they get applications, they don't realize that applications are really just word problems, and then everyone groans. But that's okay. We're going to work through these, and we're going to see how these go through. First example, we've got what looks like it's a carbon-14. Carbon-14 is a radioisometric dating method. It's only used for things that are of human origin, or like at least as long as we've been around, because after a certain age, carbon-14 starts losing a little bit of its accuracy, and they have to use other methods for anything older than that. So carbon-14 is one form of radioisometric dating, and it has the following, as this formula right here, and so there are different versions of this formula. They all mathematically work out the same. There's one involving half-life. You'll hear that term thrown around a lot. let's make sure we understand this one first. Note this is an exponential function. Note that it's got a constant right here. Note that constant is negative. The constant will always be negative when we're dealing with radioisometric dating like this, when it's of this form. What is A naught? A naught is your original amount. And then K is a constant. T is time. I believe in this case it is in years. Yes, it is in years. So what if this were in terms of half-life? Well, for half-life, you'd still have your A of T. You'd still have your A naught. But instead of having an E, you'd have like a 2, or have a half, right? And then you have a constant, but it's a different constant, K naught. Like that. And then K naught would simply be the inverse of your half-life. As a matter of fact, oftentimes you'll see it written like this instead, where K naught actually is your half-life. And so note what would happen. What happens when T equals K naught? Well, you plug that in and you'll get your original amount times 1/2 K naught divided by K naught, so that's just 1, so it becomes half of your original amount. So in this setup, that's where the half-life comes into play. Now, this constant right here, very important. This is not the half-life. This constant is related to this formula here. These are just two different ways of measuring the exact same thing. So I just wanted to kind of touch base on this. I wanted you to be aware of it because the term half-life is thrown around oftentimes, particularly if we're talking about nuclear waste or anything of that nature. All right, so let's go ahead and work this problem. We've got samples from a cave paintings in France. They contain 15% of the normal amount of carbon-14. That's the amount of carbon-14 that is present in a living organism. Estimate the age of the painting. So let's go ahead and do that. So we have A of T, and we're manipulating this formula divided by A naught, right? That is the fraction that we're looking for that we have left. Right, that is at 15%. And so that equals E KT. And so we know what K is. K is this amount right here. All right, so let's go ahead and make a quick substitution. We've got 0.15. And I'm going to leave K in that form for right now because I don't feel like writing all that multiple times, but just know that we are going to substitute that back in later. Okay, so now we want to get rid of that E. How do we get rid of that E? We're going to take the natural log of both sides. So we've got the natural log here. And so we end up with, on the right-hand side, KT equals the natural log of 0.15. And now we're going to solve for T. So T equals the natural log of 0.15 divided by our K. Let's go ahead and plug that number in now. 0.0001216. All right. So that would be as close as we can get to the answer without actually plugging it into the calculator. So let's get our decimal approximate. All right, so we get that these paintings, when you plug these into the calculator, are 15,601.3, so on and so forth. Now, this would be years ago. Now, there's something I want to point. If you were to report this number, 15,000, that's, roughly the age of civilization, I believe. It makes sense. But if you were to report this number, 15,601.3, well, you're saying that you know how old these paintings are down to the minute. Now, that would be a lie. If you reported this number like this, you would be lying. We do not know this down to the minute. This is where significant digits comes into play. We know that this painting, to the best of our measurement, has 2 significant digits, 15. So that's the number we use. So if you were to report this, you would go 15, round it to the nearest 1,000. So we would say it's about 16,000 years ago. And there are, other ways of communicating this. We could have said 15 and 0.6 plus or minus 1,000, and that would be an acceptable way to report it as well. But note that this is one way of reporting it. If you put a period here, then you're saying we know it down to the year. We do not know it down to the year. We only know it to 2 significant digits. That's as good as we know. Okay. Now let's do a different example. Example that we all have some experience with, and that example is money. So we are considering investing in an investment account that promises a 12% year rate of return compounded once a quarter. Determine how long it will take our investment to grow by 25%. So before going into this, let's talk about the compound interest formula. Note that, again, we got an A of t. And now instead of having an A naught, I have a P. And P stands for principal, right? That's the initial amount that's borrowed or loaned. And then we have 1 plus R divided by N. What is R? R is the rate per year. Okay? N is the number of compounds. Compounded monthly, N is 12. If it's compounded quarterly, N is 4, right, and so forth, so on and so forth. And this will be raised to the NT. Okay. And T is in years. Years into the term. Or it could just be the total term, if we're looking at it at the end. All right, so, and where A of t is the amount that is owed, right? So this works basically, you go through one compounding period, interest is accrued, then interest is added to the principal, and then it begins collecting interest all over again. This follows that exponential model that we were looking at before. If you might recall my joke from earlier, that the 2 kinds of people who like exponential growth the most are the insane and the economists. This is partly where that joke comes from. Now, let's go ahead and work this through, see what we have. We know that the interest rate is 12% per year. That is our R. All right, what else do we know? We have a compounded once a quarter. That means it's going to be 4. t. And now it's time to put in the rate. So we put a rate of 12%. Like so. Now, note, if you worked it through just like this, you're going to have a problem. 12%. We need to make it in a decimal format like that. So make sure you do it this way. And now for the blue, we have 25%. We don't want to make that same mistake. We're going to remember our decimal place like this, and all is fine, except that all is not fine. There is something amiss. I want you to take a second, see if you can figure out what is wrong with what I just highlighted in blue before I tell you. Here's what is wrong. Note that when we did this before, in yellow, the yellow guy up here, the yellow guy right there, when we brought it in, we just put 0.15. We didn't do anything to it, kind of like what we did here. The difference is that up here, the amount we have is becoming less and less and less. All right? If you have it set up like this, and work this through, you'll find how long it takes your investment to shrink to 25%. We do not want our investment to shrink by 25%. We want it to grow by 25%. So we put a 1 in front of it. And that would make it, and that would be what we're after, because we want it. We not only want our whole investment to still be there, we want 25% more of it to be there. So that's why we set it up that way. Okay, so from here on out, we're going to go ahead and just start simplifying. We've got 1.25 equals, and then we have over here 1.03 raised to the 4t. Now we want to get deal with that exponent. We're going to go ahead and take the logarithm of both sides. Like so. And so now we've got log of 1.25 equals 4 times t of log 1.03. Alright, so note, t is what we're looking for, so we're going to go ahead and solve for t. So t equals log of 1.25 divided by 4 times log of 1.03. Note on this step here, we used one of our rules for logarithms that we proved higher up on the sheet. All right. And I've got a strictly equals that we're going to go ahead and do a decimal approximate, because this is the closest thing we get to an exact answer. So a decimal approximate would be 1.88729. Well, I guess if you include all the decimal places, it becomes a strictly equal. But note, it'd be non-repeating. So this would be after 1.88 years. Now, it's a problem, because we want to know when will we actually have, a quarter more of the bank. Now, of course, contracts differ. Sometimes they might prorate something, but we're going to assume there's no prorating going on for this guy. And we're going to say that you don't actually get that last compound until the end of the period. So this would mean that 2 years would be the answer, right? Because our last compound was at 1.75 years, and then we have another compound at 2 years. So at 1.75, we didn't quite get up to 25% more. At the 2-year mark, note that we will be a little above 25% more, but you will not see a 25% growth until you hit the 2-year mark, as we have it set up. And that is, of course, assuming there's no prorating going on. Of course, you can have all sorts of different contracts for different types of loans and other things. So this is our 2 examples of how we use logarithms in exponential and logarithmic modeling. Have a good day.